Great, great, great. So this is what we discussed yesterday. Yesterday we discussed various, crystal growth methods available to produce silicon crystals, high quality crystals. And among all those, okay, let me also use this pointer so that this time. Yeah. Out of these, CC becomes more dominant in terms of productivity and also flexibility. And though so many other technology methods are available, finally CC based process become very dominant in silicon manufacturing, particularly. And a lot of developments, also happening recently in CC process towards the improvement of the productivity and also the quality of the crystals grown by this method, because the demand for higher quality substrate or wafers in the solar PV also is increasing to meet that higher quality. So a lot of developments happening in the growth process. We will go one by one. And as I said, so far most of the until few years before, only one crucible, normally only one crystal normally grown by the CC process. And every time you have to load the polysilicon crucible and polysilicon load, you have to empty it and you have to turn off the furnace and clean it up and put the new material. So right now, there are new processes where you can grow multiple pulls also. Instead of growing only one crystal, you can grow multiple crystal, from the same crucible by adding, refinishing the polysilicon material. That way you can produce the, you can improve the productivity and also reduce the overall manufacturing cost. So I think we stopped here yesterday. And yeah, this is the final crystal looks like, whatever be the length and diameter may change according to the requirement. The overall, crystal looks like this. So this normally we call it as a top of the crystal, and this is the body, this is the crown and body, and this is the tail. So tail part, and top part will be, normally we used to slice, because for any wafer manufacturing we need a certain size. So top and bottom, the size may not be, diameter may not be uniform. So that's why we, cut this top and bottom portion and utilize the rest of, cylindrical area where the diameter is nearly uniform. So yeah, before I get into that crystal, we will also discuss more elaborately what are the different steps involved in growing industrial scale silicon crystal growth. As I said, the polysilicon, high purity polysilicon is being used to grow the CC process mainly. And the purity of the polysilicon also, maybe a few years before, the purity of polysilicon required for silicon wafer, it was in the range of 6N to 7N. When I talk about N means 99.9999, that means 6N. And now since the quality of wafer demands higher quality, so the polysilicon raw material quality also increased. So now the polysilicon purity becomes close to 9N, 10N. So obviously the amount of impurities in the polysilicon has reduced. All the metallic impurities, which are not, which are the killers for the multicrystalline, this minority carrier lifetime. So those impurities have drastically reduced in the raw material itself. And from the polysilicon front also, a lot of developments happen how to improve the quality of the polysilicon material produced. And when you produce the polysilicon material, you can get different sizes, because you cannot, in the crucible, after you produce the polysilicon, when you fill it into the, let me turn on my video if you don't mind, so that you can also see my, right. So the polysilicon material size also becomes very important, so that a certain crucible size, if you use only big chunks, you cannot load, more amount of polysilicon. So that, for that purpose, when you, after making the polysilicon rods like this, and you have to break into different sizes so that you can pack the polysilicon into the crucible more efficient way, so that you can load more amount of polysilicon material into the crucible, so you can grow bigger size of crystals, right? These are the different, normally we call size 1, size 2, size 3, size 4, based on the different sizes, right? So next slide shows, before I go into the polysilicon, the CC process growth, I also would like to, talk about what are the different processes, for the polysilicon, high purity polysilicon growth. And this is the Siemens, though there are two different methods are available, basically Siemens based polysilicon process and also FBR based process. And mainly the Siemens based polysilicon production process becomes more dominant in the market, like more than close to 90-95% production of polysilicon is through the Siemens based process. So the Siemens based process means like where you have, allow the trichlorosilane TCS gases along with the hydrogen. Trichlorosilane gas, high purity trichlorosilane will be feed into the, high temperature CVD furnace, and then at high temperature the trichlorosilane will dissociate and silicon will deposit on the very heated rod. So there will be a seed rod will be fitted into here, and with high temperature, so the TCS will dissociate and deposit on the heated silicon rods. And based on the amount of flow and temperature and the wall cooling temperature, so the growth process also will change. So based on the growth process, you can increase the size of the rod, and each rod will be close to 10 centimeter to 20-25 centimeter diameter. So if you break this into this rod, inside you have a hairpin shape of rod, seed rod. So over on the seed rod, the dissociated silicon will deposit on that, and based on the deposition process and speed, you can get the different type of quality of polysilicon. So after this, you break into different sizes and very high purity polysilicon rods, because the quality of polysilicon rod also varies from position to position, because the bottom of the CVD carrier, where you connect the seed rod close to the electrode is basically graphite electrodes. So there are chances of graphite more carbon contamination around the contact point. When it comes to this area, probably the quality will be better. So based on the quality of the raw material, they break and they use it for different applications. So very high pure polysilicon, more than 11N, 12N purity, they use for semiconductor fab applications. And maybe the relatively poor quality, they use it for solar wafer manufacturing applications, right? So this will also once again the same thing, like before you start the process, you have to insert the silicon rods, seed rods, you have to fit into the graphite electrodes. Then the trichlorosilane gas will be fed into the high temperature CVD reactors, and it will dissociate, deposit on that, and finally it will be like this. So once you grow like this, take out, you have to cut down from the bottom, then break into pieces, then you have to pack into different sizes according to the requirement to the customer, and then you pack in the different polythene covers, high quality, then I have to send it to the customer. So why we, as I said, we cannot use only one certain size for our crystal growth purpose, because you have to pack the material as much as possible inside the crucible, because where the solid during the packaging, during the crucible filling time, and it will be full, but once it melt, automatically the amount of melt level will go down drastically off of the crucible. So then you cannot, earlier days, now you can refill it again so that you can maximize the volume inside the crucible. But a few years before, and once you fill it first time, whatever the volume comes, melt volume comes, that is the final volume. So for that purpose, probably they use different size of polysilicon, and so that they pack into the crucible in a way that you can maximize the more amount of raw materials can be loaded into the crucible one time, so that overall melt volume will be high, so that you can grow your bigger crystals. So right side, you can see this is the crucible, and quartz crucible, quartz based crucible, and how we need to fill the material so that you can pack more quantity, different sizes you have to fill. In between you have to put a small broken pieces or some granular kind of thing, so that wherever the gaps are available, these small pieces will go and fill it, so that you can maximize the loading, maximize the overall loading density into the crucible, right? So this slide shows, based on the growth process, I said, the purity of the polysilicon also will change according to the growth process. Though you are using the same Siemens-based process, by changing the process condition, growth speed, and you can change the quality. But for solar manufacturing, maybe a few years before, 2 to 3 years before, the quality of polysilicon, needs for the semiconductor application and quality of polysilicon needs for solar application was completely different. So you don't need to use the same kind of polysilicon for both the applications. So for semiconductor application, probably the growth speed is different, so that they can grow the polysilicon raw material also very high pure, 11N 12N purity, whereas solar, whether it's a CC process, or yesterday what we discussed, DSS multicrystalline process, you may not need 11N purity. You may it's okay for even 8, 10, 9N purity, so that instead of using 11N high pure material, because the environment where you grow the crystalline silicon ingot, that has a lot of contamination, because you are using graphite electrodes, graphite susceptor, a lot of graphite based carbon based materials inside the inside the furnace. So there is a chances of more amount of contamination from the chamber, the crucible, sorry, this crystal furnace itself. So in that case, even if you use a very high pure polysilicon, the more contamination is coming from the furnace. So you may not need that much high purity for solar PV applications. So that's the reason the industry also, they use, same furnace, they grow different variety of quality, and so that they can use it for different applications. So if you see from left to right, the left one is completely the density of, there is no surface, there is no popcorn structure, surface is very smooth, highly dense. So that means the amount of impurities, surface impurities, are also very less. That's why we call it a electronic grade. So EG1, it's a kind of 11N 12N purity, 99.99999 purity. So the amount of impurities like transition metal, iron, nickel, copper, those kind of transition metal quantity concentration will be in the ppb level, sometimes in the ppt level, parts per trillion level. And when you compromise the quality for different applications, so you may grow sometimes EG2 quality, EG3 quality, and when you compromise the growth process, sometimes solar application, you may not need EG1, EG2, so that industry compromise a little bit on the raw material quality, which is sufficient to get high quality wafer for solar PV applications. So if you see here from left to right, the quality we are compromising, and you are here getting here dendritic or popcorn kind of pattern. So when the more surface volume, obviously more amount of contamination on the surface, also a lot of contamination deposit on the pores between the polysilicon. So the polysilicon quality also will be less. So that means electronic grade means less amount of transition metal or any impurities, relatively lower side electronic grade. When it goes to solar grade 1, solar grade 2, and solar grade 3, the amount of impurities will be very high. So as I said yesterday also, the minority carrier lifetime of any solar crystal ingot or the wafer is based on the amount of impurities inside the the wafer or crystal. So when you are using very high quality polysilicon, obviously the output, the ingot quality also will be good, and the wafers which are sliced from the ingot also will be relatively better. So left to right, quality is deteriorating, and right to left, the minority carrier also increasing. So this is once again the same way, like how you have to load. It's a summarized way. So the crucible needs to be, before you load any polysilicon material, because the crucible has to expose to 1450-degree temperature. The quartz crucible, which is a thickness of 22 centimeter or 1.5 to 2 centimeter, 15 to 20 mm or 25 mm wall thickness, and you have to ensure that the crucible doesn't have any kind of flaws or micro cracks before you start loading, because if there is a micro crack at high temperature, probably the crucible may get cracked further, and the molten silicon will come out from the crucible and damage the entire furnace, and sometimes it leads to explosion also, because very high temperature at 1450 1500 degree, when silicon comes out and react with the furnace material, so automatically, because your furnace is having the water cooled jacket, when the silicon, the molten silicon comes out contact with the furnace body, and it damage the furnace body, the water which is flowing on the furnace, it may come inside. When water is comes exposed to 1500 degree, obviously hydrogen will be generated. There is a chances of explosion also. So the quality of the crucible, before you start loading any material, it has to be ensured there should not be any kind of micro cracks or any flaws and all those things. Then you have to load the crucible. Once you load the polysilicon material in a way how to pack it maximum, then if you see here, we are loading some dopant material. So this is the dopant material. We have to add, this amount of dopant. This dopant it may be a boron or a gallium or phosphorus. So you may ask why we need dopant. Normally, when you grow the high purity polysilicon, and the conductivity, it becomes very non-conducting material. Whereas for solar PV applications, we need to create a p-n junction. So we have to, either we need p-type substrate or n-type substrate to create the p-n junction or np junction. The pure polysilicon, the raw material, pure polysilicon is an insulator. When you grow in a rod shape, very high pure, and it's an insulator, we have to convert this polysilicon into the conducting nature by doping either p-type based dopant or n-type based dopant. So for p-type, mostly we use boron. Boron is a trivalent. When you dope boron, the grown ingot becomes p-type. From insulation to p-type. When you add phosphorus dopant into the polysilicon during the growth process, the grown ingot will become n-type. So the crystal is n-type. Whatever the wafer you slice from out of that crystal also will be n-type. And then if you use n-type as a substrate, you can make np junction, solar p-n junction, so that you can produce the solar cell devices out of this wafer, right? So after you fill all these things, then all the crucible, because as I said yesterday, the crucible also after 1000 degree, the crucible become very soft, and you have to protect with the succeptor. The crucible will be placed inside the succeptor. Then there is a water cooled chamber. Then there is a heater at the bottom and top and side also. So it will heat the complete this hot zone area. Then polysilicon which is inside the crucible also gets melted. Okay, so after filling, it has to be closed properly. Even filling also should happen in a very controlled environment. You cannot load it in the normal atmosphere where a lot of dust, the dust control is very important while loading, because you are using 10N, 11N purity. And if you load it in normal atmosphere, a lot of dust may fall into the this one. So you have to load in a very controlled environment. Then after that, you have to close it properly and load into the furnace directly. So these are the coming slides will show what are the different steps involved, before you get a from polysilicon raw material to before you get a very good, long and round crystals. So this is the crucible. Then we have to load this, high quality, maybe the amount of polysilicon load into the crucible. It may be 400 kg to 500 kg at a time. So we have to load this, crucible in a proper way inside the furnace, right? And once you load the furnace inside the furnace, then okay, maybe you can see. Some background noise is coming. Can you ask everybody to mute it?
Hello, everybody is mute disturbance.
Yeah.
Kindly mute yourself.
Okay. So after you load this one, then we have to use the seed rod, because a CC process need the seeding process, whereas the one we discussed yesterday, it doesn't need any seeding process. It's a forced cooling process. After melting, you force the cooling so that crystallization starts from bottom to top. Whereas the CC process, where you have to insert, we have to use the seed with a certain orientations. And seed also, there are different shapes of the seed. And seed orientation is also very important. And seed, the conductivity is also very important. And you can get the seeds in different shape from the market, or whatever the crystal you grow, you can also create the you can make the seeds from your grown crystal by cutting as per the size you want, right? So this is the initial seed. Normally it will be like this. It will be feed into the chuck, so that the seed will not fall down, and it start melting and make a contact with the melt. And it can hold even the crystal of more than 300 kg or 400 kg of crystal weight, a small seed. And once you start using the crystal seed, quality will be like this. Initially it will be like this, and after usage the bottom side will be like this. So this is the dopant. This is the dopant. As I said, the pure polysilicon is an insulator, and whatever the crystal conductivity you want based on the applications. So either if you want P-type wafer, then you have to grow P-type ingot. If you want N-type wafer, you have to grow N-type ingot. So you have to add the suitable dopant into the polysilicon during the crucible loading process, suitable amount of dopant, whatever the resistivity you want. And by adding suitable amount of P-type dopant and N-type dopant, you can maintain the resistivity. You can get the desired resistivity range across the length of the grown ingot. So for P-type, if you want to P-type crystal, generally gallium or boron, maybe 2 to 3 years before, boron was the major main dopant used for P-type ingot crystals. And now recently gallium started industry started using 100% gallium, and replacing the boron. There are some reasons why gallium has come into the picture, why boron cannot be used. So when you use boron, so because in the grown crystal also have some oxygen. When you have a boron dopant, the boron oxygen pair will be generated. So when you have a boron oxygen pair inside the crystal as a impurities, and there is a that also minority carrier lifetime, it will deteriorate the performance of the crystal quality, because it captures the minority carriers, the boron oxygen pairs. So to minimize that boron oxygen lifetime killing zones, so industry started using gallium, where gallium, boron is completely replaced, so that there won't be any boron. So even though if you have oxygen, since there is no boron, there is a zero chances of boron oxygen pair which can deteriorate the minority carrier lifetime. So that's why last 2 years or 3 years the industry is completely using 100% gallium as a dopant. to grow p-type silicon ingots. So for n-type, I think phosphorus is being used at the day one, and some companies, they started using arsenic and antimony, but still, once again, it's a kind of very expensive material. So mostly industry, 99% they are using only the phosphorus based dopant to grow n-type silicon ingots. And purity of this dopant also should be as high as possible, because you are going to add this dopant material into the 7N, 8N, 9N purity polysilicon. So purity of this material also very, very important. So another important, after you load into this one, you have to add barium carbonate powder. So what is the use of barium carbonate powder? When you load this one, the crucible wall is a silica crucible, and after melting, the silicon will have a direct contact with the crucible wall. And since it's a silica crucible, there's a chance of SiO2 based crucible. There's a chance of lot of oxygen may diffuse from the crucible into the melt. So, and also not only that, and also to avoid the melt directly contacting the silica crucible wall, so they use some barium carbonate. So once you put the powder into the while loading the polysilicon, and after melting, the barium carbonate will make a small wall kind of thing, so that the barium carbonate between the silica crucible and the molten silicon, the barium carbonate will make as a barrier layer, so that the it will minimize the direct contact of molten silicon into the silicon, the quartz wall, and also minimize the infusion of oxygen content from silica crucible to the molten silicon. Right, because oxygen also, as I said yesterday, oxygen quantity also, concentration also should be as low as possible. Since we are using silica based crucible in CC process and also the previous DSS process, so amount of oxygen infused from crucible wall into the molten silicon is unavoidable. But still, by putting this kind of protection layer, you can minimize the amount of oxygen coming into the melt. You can minimize it, so that overall oxygen concentration into the crystal also will be less, so that the wafer which you are slicing from the crystal also will be downside, so that you can minimize the overall oxygen concentration. And also, if you use gallium instead of boron, so boron also you are 100% removing, and oxygen also you are removing the concentration. So overall, the minority carrier lifetime also will get enhanced by doing this. So after you load the entire crucible into this one, then you have to start heating the material. So the polysilicon material which is inside the crucible start melting slowly. Then after some time, it will be like this. So then you have to insert the seeding process. This is very important process. After you ensure that complete silicon got melt, then you have to dip this seed crystal into the molten silicon, and this is the first step. Sometimes the temperature is very high, the silicon temperature very high, it can melt the seed also. You cannot establish the interface. So establishing the interface is very critical for the quality of the crystal, because you're putting the seed into the molten silicon. If the temperature is very high, it will melt the seed. So you then accordingly you have to adjust the temperature, and you have to rotation everything. You have to establish that good contact between. And if the temperature of the molten silicon is very low, once the external seed touches the melt, automatically the crystal silicon starts solidifying. That also should not happen. You have to, the solidification or crystallization should happen in a controlled way, so that you can maintain the crystal quality. So this process, necking process, dipping or necking process, is very critical. One of the very critical process to determine the quality of the ingot which you have grown. The ingot quality is good. Obviously, the wafer which are produced from the ingot also will be very good. So for that, when the seed, if as shown in the previous slide, the seed size. So when you dip it, And the seed also seed also has a lot of impurities, not impurities, and dislocations also. So when you make the seed start making the crystal, the dislocation exists in the seed crystal should not transfer to the crystal. So for that, even though the seed size is 8 or 1 centimeter diameter, finally you have to make a very thin neck, the 10 centimeter, 10 diameter. Finally it will melt it, so that when you pull the once you establish the proper equilibrium condition, then you start pulling the seed, and seed also will melt the diameter from 10 to finally it becomes 1 or 2 Then after that you start making the process, so that you are minimizing the transfer of all the dislocation which dislocations are existing in the seed. You are minimizing the transfer of dislocation from seed to the new baby, the crystal. This is the way you have to control. This is the very critical process to control the quality. So once you establish the 10 seed will become 1 or 2 then you start the growth process, adjust the temperature, the process, so that you can start, making the crown process. Then you can make the crystal. If you see here, so instead of making one attempt, you melt it, then slowly big it, then melt it slowly. So you can make a small, ups and down, so that you can minimize the dislocation exist in the seed crystal. You can minimize the transfer of dislocation from seed to the new baby crystal, which you are, which is growing, right? So this is once you establish that process. If you see here 10 size, finally it becomes 1 2 around this area. Once it becomes 1 2 then you start the necking process, crown process. Normally you start establishing the crown process. Then you can increase the adjust the process settings, so that the crown will become the neck, then crown, then becomes body will start. Right. So once the body will start, then you can control the diameter, because you start adjusting the crucible rotation and the seed rotation, seed pulling speed and rotation pulling speed and temperature. And by controlling all these parameters, you can define the crucible diameter, sorry, this crystal diameter also you can control it. And earlier it was a manual process where the operator has to look at the crystal through the weaving window, and whenever the crystal diameter goes higher side, then he has to adjust the parameters to maintain this one. So sometimes because of some process parameters, so the crystal diameter also will go slightly lower than what you said. So it was a manual process, but last maybe I would say 10 years, the industry set up a camera. So automatic camera can detect the diameter, and automatic ADC based automatic diameter control. So the camera will set the diameter, set the condition. The camera will see all the size of the diameter of the crystal, grown crystal, through different cameras. And whenever the diameter goes away from the set value, so automatically the process parameter will change, like a temperature, pulling speed, and rotation speed. Everything will automatically adjusted to ensure the diameter is well controlled within the limit. So this is the way they can control the diameter of the grown ingot. And whatever the diameter you want, like 200 diameter, or 270 diameter, 250 or 300, according to the wafer size you want. Maximum so far the industry has achieved, PV industry maximum 300, whereas the semiconductor, I think what I understood, as far as I know, they have grown even 400 diameter crystal also. Whereas the PV application, mostly industry gone to 300 because there is a limitation, because semiconductor you need large size wafer, so that you can make many devices within that wafer surface. Whereas in the PV, even if you have a large size wafer, you cannot, because in semiconductor you can make thousands of devices in a single wafer. Whereas here one wafer means one device. So if the wafer area increases, automatically the losses also will increase. Whatever the carrier generator, it has to travel long distance. So obviously we need, smaller optimized size where you can get more power at the same time less losses. So PV application maximum diameter so far is 300 diameter is the industry is using, whereas semiconductor industry already achieved 400 diameter crystal. And also semiconductor normally use a round size wafer, and orientation is also different. And the solar PV also round crystal wafer, but from there you can cut the square wafer or rectangular size wafer as per the requirement. So once you grow the body to a certain length, so obviously the amount of melt inside the crucible also will go down. So once you ensure that maximum, suppose 300 400 kg of molten silicon is available, so once you ensure that amount of 350 kg of silicon already converted, molten silicon converted into the crystal, then if you feel that last only 20 kg which has a lot of impurities, because normally the polysilicon, even though it's a very high pure, during the 2 days 3 days continuous growth process and lot of contamination from the crucible in the furnace environment, since we are using a lot of graphite carbon based material, and also a lot of impurities diffused from the crucible, the quartz crucible also. So all these impurities will try to stay in the molten silicon only. So because of that, when silicon molten volume goes down, the amount of impurities in the molten silicon also will increase. So the last portion of the silicon melt, I will have a lot of impurities. So the ground, obviously the crystals grown from the last part of the silicon also has relatively poor quality. And when you make the wafers out of that particular area, probably the minority carrier lifetime also will be very low. Also the not only the impurities, also the oxygen concentration across the length of top to bottom. The length of the crystal also you can change according to the amount of silicon you are loading into the crystal, you loading into the crucible. And also diameter, when the diameter increases, probably because your volume is fixed 300 kg or 400 kg of silicon you loaded, and if you increase the diameter, the length of the crystal will come down. Or if you minimize the diameter, then maybe you can grow even longer crystal, even up to 5 meter or even 6 meter also industry has already achieved, right? So whatever the left out material, maybe few kgs, finally we cannot convert all the molten silicon into the crystal. The final portion, few kgs, we have to leave. That normally we call it a pot scrap. As I said, this material has a lot of contaminants or impurities, so we cannot use this one. Maybe we have to take it out and then use it for some different applications. Maybe steel industry, they this kind of purity is okay for different applications. We cannot use it for solar PV again. So this called as part scrap. So now normally 1% 2% of the material will be waste as a part scrap. So if you see here, after the one growth process, see the the surface of the crucible. Here where there is no, because you have loaded up to here initially, before you start melting, the polysilicon was loaded up to here, but after melting, the overall polysilicon, the molten silicon level has come down even 1/3 of the crucible, or even 3/4 of the crucible height. And then when you start pulling, the amount of silicon in level also goes down. And finally, this area, where the molten silicon is in contact with the the quartz crucible for a longer period, so that coating also deteriorating. So you cannot, once you cool down, and you cannot use this crucible again. It's a one-time use. So that's what I'm showing here. So whatever the crucible, it becomes only after you pull the one crystal, whatever the length and diameter, as per the volume you load it, and you have to stop the furnace and clean it up and put the new crucible, load the new charges, and you have to start the new process. So this is the overall, it will be like this, how it will be unloaded after you grow the crystal. and you have to cut down this process. This, then you have to take out this top side separately, and you have to turn it and take the crystal out. Then you have to load the seed again. Then meantime, you can also fill the raw material inside through different different apparatus. And then once you unload this crystal and load the new seed, then put it back again, then you start doing the crystals. So if you see here, this is what, in the grown crystal, normally we call this is as a seed cable. It is, it is measuring the weight of the overall, the how much molten silicon converted to the crystal seed cable. And this is the seed holder where the seed rod initially will be, uh, fit into that seed holder. And this is the ingot where you can see the very thin, very thin, the silicon seed rod size also become 10 mm size, will become 1 mm, 2 mm. This 1 mm, 2 mm will hold the entire, 300 kg or 400 kg of silicon ingot. And as I said, earlier only one time. Now you can, once you take the grown crystal out, meantime you can also charge the crucible. The crucible, you will not empty it. You will keep only 1/3. Maybe if you 300, 400 kg initially charge will be there. You grow only 200 kg, 250 kg. Remaining 150 kg will be left on the crucible in the very hot condition. And once you take the crystal out, then parallelly, you have to load, after you remove the grown crystal out, then you have to charge the silicon again, meantime, through this device, so that continuously you can also refill the crucible. Crucible is in a hot condition, so you can refill the crucible. Another 100 kg of polysilicon you can load into the crucible, so that overall volume 150 kg becomes 250. Then again one more time the 250 become 400. So once again the crucible volume becomes same like what the initial, how it was in the initial stage. So even after growing the crystal, without shut down the furnace, you can load the charges again, and you can grow one more crystal. So by this way, you, instead of one crucible one time, that was 5 or 6 years before, now industry is doing 5 to 6 crystal at a time. So that only 400 kg earlier, one crucible 400 kg one time, now 2000 kg of material you can use using one crucible. So that you can, overall you can minimize the overall, downtime of the machine, and you can grow more number of ingots in shorter period of time, and crucible life also extended. Instead of using 5 crystal, 5 crucible, now one crucible, 5 crystals. So crucible is one of the costliest, raw material into the manufacturing process, so that you can minimize the overall cost of the production. So this is the way the industry is working right now. Instead of single crystal, they are doing a recharging crystal. So this is the one, after you grow, as I said, top side and bottom side, the parameters of, the crystal quality, diameter change, or oxygen or carbon concentration, and resistivity also. Since you are doping the p-type boron or gallium or phosphorus, you are doping into while, loading the polysilicon, so that crystal will become n-type or p-type. The resistivity also will change from top to bottom based on the segregation coefficient of the dopant. Suppose the segregation coefficient is very low, the dopant segregation coefficient is very low, automatically the amount of all the dopants will stay mostly on the molten side. So the grown crystal will have only less amount of dopant. So the top side, the resistivity always will be higher, because amount of dopant in the top initial stage will be very low. So when the dopant concentration is very low, the resistivity is very high. Same time when the crystal grown like this, then amount of dopant into the molten silicon is increasing, so that bottom side, from top to bottom, when you see the dopant concentration also will increase. When the dopant concentration increases, automatically the resistivity also will be downside. So for example, if your set resistivity is 0.5 to 1.2 ohm centimeter, if you want to grow the crystal in this particular range, the top side will be 1.1 ohm centimeter. And when it comes to the bottom of the crystal, the resistivity will become 0.5 or zero point 0.6 or sometime 0.4 also, because the amount of dopant in the bottom side relatively higher side than the top side. So the resistivity also will change. Not only resistivity, the impurity, the oxygen, interstitial oxygen, and carbon concentration also, top to bottom also will change. Particularly carbon, in this particular CZ process, carbon concentration will be relatively less, even though we are using so much of carbon components inside graphite electrode and graphite susceptor. Still amount of carbon going into the molten silicon is relatively less, because you are using argon environment. The growth process will be under argon atmosphere. So the amount of carbon particle get into the melt is relatively less, whereas the amount of oxygen going into the molten silicon is very high, because you are using quartz crucible. So amount of oxygen diffused from the quartz crucible, and also since you have a carbon, and carbon monoxide also will be formed, and carbon monoxide once again converted into oxygen. So amount of oxygen concentration in the molten silicon will be also to change. And from if you take the oxygen profile from top to bottom, so initially oxygen profile, oxygen concentration is very low, then going forward oxygen concentration is very less. But end of the crystal, the tail side, the oxygen concentration will be very high. Why? Because the amount of oxygen, the amount of molten silicon available in the crucible is relatively less, whereas the amount of oxygen into the from the different from the crucible wall also more amount of oxygen in the less amount of molten silicon. So oxygen concentration in the molten silicon is high, so that bottom side you have more amount of oxygen, which is not good for which is not required. So the oxygen and carbon concentration profile also from top to bottom will change according to the growth environment, and according to the process parameter, how fast you are pulling and how big you grow the ingot, and all those parameters will determine the all these three parameter: resistance, resistivity variation across top to bottom, and carbon and oxygen concentration, right? And as I said, so how to measure the oxygen concentration? Because the resistivity, of course, you can measure by non-contacting method. If you touch here, what is the resistivity? You can measure it here, 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 here. And we have defined the resistivity what we want. And if any portion of this, any part of this crystal grown, if it is out of our requirement, then you have to slice. We cannot use that for our end use application. So you have to cut that part, and you can throw it, or maybe you can reuse it, because you can reuse these grown pieces also. Again, it's a raw material for the next growth, but you cannot use 100% this recycled material. Maybe 10-20% of this recycled material you can mix with a good 80% of the pure polysilicon, so that you can reuse this material also. You can minimize the overall polysilicon cost also, right? So, as I said, the oxygen concentration we need as low as possible. And because more oxygen concentration into the crystal ingot, the sliced wafer also will have more oxygen. More oxygen means there is a chances of LID, light induced degradation. When you use boron, as a dopant, as I said, boron and oxygen will form a boron-oxygen pair, and that will deteriorate the overall minority carrier lifetime. So that the degradation initial days, the overall solar, if you make the wave solar cell out of this high boron oxygen concentration, the initial degradation will be relatively higher side, which is not uh, required to the end use customer. So if you see here, the resistivity also, because this is the almost, you can say, almost 6 number of crystals you have grown in a single ingot. Instead of single crystal, we have used 6 times we pull the crystal. And what is the resistivity range, for each crystal? And normally, 0.4 to 1.1 is the resistivity range we decide for the solar cell applications. Whereas 4 or 5 crystals, you can maintain the similar kind of resistivity. But when you increase the number of crystals, automatically the amount of the dopant or amount of impurities into the last crystal will be relatively very high, so that you cannot control the resistivity of the last crystal. Not only resistivity, overall the entire impurity concentration like oxygen, carbon, and also the metallic impurities of the last crystal will be very relatively poor, because the molten silicon you are adding again and again, and the impurities always settle down in the left out molten silicon. Then you are adding one more polysilicon again. So second time also the molten silicon relatively, the molten silicon has relatively higher concentration of impurities. Third time further higher side. Fourth time higher side. So when you grow the last crystal, the amount of impurities on the molten silicon is relatively higher side, higher than the first time you are loading into the polysilicon, right? So obviously the last crystal has relatively poor quality in terms of resistivity distribution, and also the oxygen concentration and minority carrier lifetime in all aspects. So N-type normally, P-type normally the desired resistivity range is 0.4 to 1.1, where you can get the suitable higher efficiency at cell level. And N-type based device, suppose if you are going to grow N-type wafer, then you have to make NP junction. So for that, N-type wafer resistivity is a requirement is some manufacturer they use 2 to 7 wide resistivity range for N-type. Some manufacturer they use 0.3 to 2.1 and something like that. So most of the industries they use, whenever they grow N-type ingot, the resistivity range also wider comparatively in compared to P-type. The N-type ingot has wider resistivity range because you are using phosphorus. So phosphorus, the segregation coefficient of phosphorus is very, very low. So when you add the phosphorus as a dopant, the phosphorus will always stay into the molten silicon, not into the not get into the crystal grown ingot. So when less amount of phosphorus get into the silicon, grown silicon, automatically you have a higher resistivity, right? Because the phosphorus has lower segregation coefficient compared with the boron and gallium. So this is the reason when you grow N-type crystal, the resistivity range across the crystal length also wider than the P-type crystal ingot. And if you see here, the last crystal, if you see the resistivity is going out of control. So probably we have to last crystal, we have to cut this area, and we have to we cannot use this entire crystal length for the next processes. So we have to cut this area. When you cut after grow the cylindrical ingot, if you cut a certain portion, automatically your overall conversion yield also will go down. That will impact your cost of manufacturing. So all these parameters are very important. How control you grow the resistivity, oxygen concentration, carbon concentration, and minority carrier lifetime without losing any parts. So that whatever the crystal you grown, you have to convert into the next process instead of slicing and recycling it. Of course, you can recycle most of the parts you cut from this grown ingot, but recycling, of course, you can use it, but still your overall conversion yield will go down. That will impact your manufacturing cost. And this table shows what kind of different technologies, cell technology, and what kind of resistivity wafer normally they use for this technology, and what was the dopant they use, and what was the earlier resistivity, and how the industries changing their requirement in terms of resistivity, and in terms of minority carrier lifetime, and in terms of carbon oxygen concentration also. So maybe a few years before, the technology was different. At that time, the requirement of wafer was different, quality of wafer was different. Now, when as I said yesterday, the efficiency of the cell technology also going very high, even 25% efficiency, 26% efficiency. So obviously, they need very high quality wafer with a certain resistivity range, controlled resistivity, and certain amount of impurities. Impurities also should be as low as possible, and the minority carrier lifetime also should be should higher than the previous person. So this table shows different technology. Monoper technology, which is the p-type based, the conductivity type of wafer is a p-type, and the gallium is the dopant normally used. Maybe 3 years before boron was there. Now boron is 100% replaced by gallium, so that you can minimize the overall boron oxygen pair, so that you can minimize the degradation in the field. After you convert the cell into the module, when you install these panels into the field, initially there will be a 2%. Initially, once it's exposed to the sunlight, there will be a 2% degradation right away within a month time. And if you replace the boron, if you minimize the oxygen concentration, then the same kind of per module, if you put it in the field, instead of 2% degradation, the degradation comes down to 1%. That means you are significantly improving the generation degradation percentage, so that you can life of the product also will be extended. So gallium is the dopant, and resistivity was 0.4 to 1.1. Still, they are maintaining the same resistivity. And if you see the minority carrier lifetime for p-type, which is 70 microsecond, right? And even now also they are maintaining, and some companies they demand even 100 microseconds. And oxygen concentration, there is no major change. But when you go for high efficiency technology, TOPCon, and even TOPCon is the currently mainstream high efficiency technology, and HAT, all these new technologies are based on N-type product. They are not using p-type based substrate. So that indicates that maybe a few years before, all the grown ingots are p-type. Now the entire industry is moving, entire industries are moving from p-type ingot growth to n-type ingot growth, because n-type based wafer technology is offering higher efficiency. So p-type based technology probably in another 2 to 3 years will be phased out, and n-type based technology will dominate into the market. Right, and the dopant is a phosphorus. Phosphorus is so far, phosphorus is the main dominant dopant being used, in the TOPCon technology and HGT. Of course, there are p-type based next back contact technology also. People are exploring once again p-type, but probably n-type will dominate over p-type, and most probably all the future technology will be n-type based wafer. So that means you have to grow the n-type crystal by doping phosphorus as a dopant, and resistivity range also relatively wider. And if you see the lifetime, earlier the n-type, the crystal, the whatever the crystal you are growing, the minority carrier lifetime will be 800 microseconds. Whereas the p-type, the minority carrier lifetime is very poor, 70 microseconds. When you grow n-type ingot, same kind of polysilicon, you can get very high purity, very higher minority carrier lifetime. And HJT, they need 1000 microseconds, that means 1 milliseconds lifetime. And now, because efficiency is increasing, demand of wafer quality is improving, increasing. So obviously 800, now some companies they have started using 800 is not sufficient. Minority carrier of 800 microseconds is not sufficient. They need even higher minority carrier lifetime. So some cases even 3000 microsecond also. If you see here, TPC back contact technology, they need 3000 microsecond based lifetime quality. So obviously the demand for higher quality wafers increasing. So because the technology needs higher quality wafer, so that also depends on what kind of material you are using. If you use very high pure polysilicon material, 9N, 10N, obviously the end product also, and also different growth conditions also, you can get very high quality wafer also. Right. So this is all about the, after you convert into ingot, then how you are going to convert the ingot into the wafering process. There are different processes. Yesterday, I think the previous one of the presentation they talk about semiconductor wafer processing. Here I'm not going to talk about semiconductor wafer processing. Here I'm talking about only the solar PV, how the solar PV wafers are being produced from the cylindrical ingot, right? So after you cut the top and bottom, tail and head, and you will get a 3 meter, 4 meter length of cylindrical rod with a uniform diameter. Then you cannot use carry the entire 3 meter, 4 meter. So you have to cut this into 800 centimeter, 800 mm, 80 centimeter in different 3 or 4 pieces, and these pieces is a cylindrical form. Finally, you want either square wafer or rectangular wafer. So then you have to cut this into this cylindrical form will be converted into square shape by cutting all the 4 sides, so that you will get pseudo square of this kind of thing. Right. So for that, once you prepare this, this brick, then how to make the slice? So finally, you have to this edge chamfering also has to be done, because edges should not be very sharp. When the edges are sharp, when during the some handling process, if they hit each other, there's a chances of breakage, micro crack generation. That's the reason the edges will be chamfered, slightly tapered. This one. So after you make the brick, you have to convert this brick into different size of the wafer. So for that, you have to fix this brick into the different plate. There is a glass or ceramic plate normally used. So over on the glass, thick glass plate, you have to take the glass plate and put the adhesive over on the glass plate. Then you put this brick, whatever the brick you want to cut into wafer, wafers, you have to fix that brick over on the glass plate. If you see here, this is the glass, this is the glass or ceramic plate. You have to fix this brick which you want to convert into wafer. Then this plate again fix with another plate, so that then this plate will be fit into the machine, so that entire brick, after maybe a few hours of curing, after you apply the adhesive, you have to wait for 4 hours or 5 hours, so that adhesive will be cured and it can hold the entire weight of this brick. Then this brick will be loaded into this machine, where it will be like this. So this is the machine where you can load this entire brick. Then the holder will be here, the brick will be hanging, and it will be held by this glass plate and adhesive. Then it will be like this. Then there is a 2 pulleys. The wires will be winding, unwinding, and winding again. So this this brick will slightly slowly will move from top to bottom. So top to bottom, these wires having some slurry, some abrasive, particle embedded on the wire. When the and also water or glycol mixed, water will be poured on these wire. And when the wires also continuously moving, this will slide, slowly will move down. And when it touches the wires, will slightly, will start cutting this wafer as per the pitch, the wafer thickness, whatever the thickness you want, 200 micron you want, 300 micron you want, 400 micron, whatever the size you want, you have to define the pitch of this wire. Suppose based on this wire only, you can get the desired thickness of the wafer. And of course, wire thickness also plays a very key role, because each and every wafer, because one wire, two wire is going like this. So in between the whatever the silicon, it will become converted as a wafer. So when the wire diameter is very high, then when you cut it to make one wafer, you have two diamond wire will slide that one. So when the diameter of the wire increases, automatically that amount of silicon will go as a slurry. So that's what yesterday we discussed. Whatever the silicon, the cut silicon powder will be generated during this process will be collected and used for battery applications. This is the pure silicon. And this is the wafering process. And if you see here, after wafering process, it will be like this. So whatever if you see here wafer, the wafer thickness will be 200 micron, because the glass plate, the first of all, the brick was fixed with the glass plate through adhesive. So after the wire cutting up to here, once it touches the glass plate, the process will stop, but still the wafers, the cut pieces are holded by that adhesive. So then once you take it out, after completing the process, you take it out, then put it in the hot water, automatically the adhesive, where the adhesive which is holding the entire cut wafers, it will be soft, become softened. Then you have to take out the wafers very gently, slowly. take it out, then you have to put into the water, then you rain with bubbling kind of things, so you can separate out, individual wafer also, right? So after that, the wafers will be like this. Once you remove from here, the wafers will be like this and completely cleaned up. Then you have to multiple levels of cleaning, because the wafer surface, because it has contacted with the glass plate through adhesive. Even though it is detached from this plate, the surface may have some small amount of adhesive, the polymer material. So you have to clean that properly before it goes to the next process, solar cell manufacturing process, or before you send to the any customer. Otherwise the quality, it will contaminate the otherwise you may not get the desired cell efficiency. So a lot of so many other cleaning process after this cutting process will happen. So this slide will tell you the summary of entire whatever I am discussing. This slide will show you the complete summary, because you have to grow the crystal like this. After you cut the grow the crystal, whatever with the length, 2 meter, 3 meter, 4 meter, and decide diameter, you have to cut the crystal into, you have to remove the top and bottom sides where the diameter is not sufficient to convert into wafer, and also the quality of the top side and bottom side may not be as good as the body part. So you have to remove that one. After you remove it, you cut this into 800 size, because you cannot use 2 meter 3 meter length as a next process. You have to cut into 800 to 900 size. Then you have to feed like this. You have to fix with the two support rods. Then you feed into this one. There is a wire. Again there is a wire is there, so wire will cut like this. So when it goes into the cylindrical form, then the wire will go like this. Then once again the stage will rotate, the wire will go like this, so that when it comes out, all the sides, the cylindrical crystal will become square shape after removing, cut the pieces. So all these cut pieces you can use it for recycling. It's a good quality, and we can use it for reprocessing to the next time when you load the crucible. You can use some quantity of this one, not the entire quantity, maybe 20% or 15% you can mix with the pure polysilicon, so that you can optimize the charge and amount of polysilicon, so that you can minimize the manufacturing cost, right? So this is the process. Finally, you have to convert into wafer. The wafer will be converted to solar cell. The solar cell will be converted into module. So the right side will show you again the same process. Like as I said, whatever the thickness you want, you have to maintain the pitch of the wafer, the wire, the pitch you have to define. If you want 120 micron wafer thickness, you want 150, 180, or 200 micron. Accordingly, you have to design the pitch of the wire in the roller, so the wire will get into the brick and cut the wafers. And if you see here, this one is like a wafer thickness, for example 200 micron, and you have that this is the diamond wire. For example, this is the diamond wire. So diamond wire thickness is, let's say for example, you want to produce 200 micron wafer thickness. I want a wafer of 200 micron thickness. So how much you are losing? The wire thickness, suppose the wire diameter is 150 micron, this wire only will start from here to here, right? So all this entire 150 micron wire area, the silicon is going as a waste. So for to make one 200 micron wafer, you are wasting 150 micron equivalent amount of silicon as a loss, kept loss. Of course, right now you can use that powder as a for battery application. Still, you are almost using almost equal amount of silicon to produce one wafer. You are wasting almost 70%, 80% silicon as a kept loss. So that's the reason now. Earlier maybe 150 micron thickness diameter wafer. Now the wire diameter has come down from 120 micron maybe 10 years before. Right now the wire diameter is 30 micron, 40 micron. So that to produce 200 micron, you can use 35 micron or 40. So you can use 40 micron or 35 micron wave wire, so that amount of silicon loss, kept loss, also drastically reduced from 120 micron to 30-40 micron. So so that you can produce more number of wafers by using a smaller diameter wire. But at the same time, when your wire diameter goes down, the strength also need to be improved. Otherwise, when the wire goes into the silicon, the strength is not good, the wire may cut. Then you have to take out the entire process, you have to change the wire. It's a tedious process, right? So you have to ensure that while reducing the wire diameter, at the same time you have to ensure the strength of the wire, and where it should not break in between the process. So this slide, okay, this is the wafer process. This slide, going forward, I'm going to talk about what are the different improvements are happening in the wire side. And if the ingot side maybe furnace is 1600 2023, the furnace diameter, the crucible furnace diameter 1600 mm. Now going forward 2030, probably they are also talking about automatic continuous CC puller, where you grow the crystal, you don't need to refill it. You take it out, refilling. You grow the crystal continuously. You feed the polysilicon into the crucible, so the level of the melt level always will be maintained. There is no kind of level will go down, then refill it, bring it up, then go down, refill it. That's a recharging mechanism. Now there's a new mechanism called continuous CC. You grow the crystal, same time the double crucible concept, where the inner crucible the melt will be there, the outer crucible you pour the polysilicon, very fine powder, kind of a small pieces of polysilicon, so that the polysilicon will get melt and maintain the level, so that you can grow the crystal and continuously pour the polysilicon material, so that you can minimize the you can minimize the downtime, and you can produce more number of crystal, and you can maintain the level, so that concentration of all the impurities also will be relatively less. So that's what happening in the future. Maybe another 2 to 3 years, we may expect further improvement in the crystal growth process. Earlier it's one crystal, one crucible, one crystal. Now change to recharging again, so that one crucible 5 to 6 crystal. Probably going forward, one crucible maybe 10 or 15 number of crystals, and also improved in terms of all parameters. And in the wafering side, the wafer thickness also has come down. Earlier it is 200 micron. Now it's a 2023. The average wafer size is 140. It is expected the wafer size also become thinner and thinner. When the wafer size goes down, amount of polysilicon need maybe 1 centimeter or 1 centimeter of brick. You can earlier used to get maybe 100 wafers, including the losses. But when the wafer thickness goes down from 200 micron to 100 micron, the same 1 centimeter you can get even 200 or 150 numbers of wafers. So same area, when wire thickness goes down and the wafer thickness goes down, you can produce more number of wafers, right? So this is the the way the technology is moving, so that you can effective utilization, you can minimize the wastage of silicon. Otherwise you are growing the big ingot, converting the round into square pieces, then you cut into square pieces into wafers. While slicing process, almost 50% 60% silicon going as a kept loss. And now in this case, by doing this, the 50% 60% will become to 10 to 15% loss. Of course, you cannot avoid the losses, but you can minimize the losses, so that overall conversion efficiency, polysilicon into final wafer, that you can improve it, so that overall you can minimize the wafer production cost. So if you see, this is the wafer thickness with the different technology. P-type wafer, mono PERT, wherever you use P-type, the wafer thickness is right now 150 160 micron. It is expected not much down even after 2025 26, another 2 years 3 years, it will be 135 or 150 to 135 range. Whereas in the n-type TOPCon, n-type based technology, the wafer thickness is already 130 already we are in the 125 130 micron, and it is maintained the same. And whereas the another technology, HJT, another cell technology, where you can use even low thickness wafer, it is already industry started using 110 micron. it is expected the wafer thickness will go even below 100 micron wafer you can use for solar cell manufacturing. Yesterday also we discussed, the crystalline silicon wafer thickness 150, 140 micron, whereas there are some methods where you can grow the wafer to gaseous phase, gas into the wafer conversion, where the thickness will be few micron, 10 micron, 15 micron wafer thickness. So now the HIT technology is a relatively low temperature process where you can use very thin wafers. So by using this technology, the silicon, amount of wafer thickness goes down, your wafer price also will go down because you are effectively utilizing the silicon instead of wasting. And you can produce 1 centimeter instead of 100 pieces, 100 wafers, you can produce 150 in the TOPCon case, whereas the HIT case, when wafer thickness goes down, wire thickness same, but wafer thickness goes down, you can produce 175, 180 numbers of wafer in the same size of brick. So obviously, your production cost also will go down, right? And this is the one, as I said, right now we are growing round crystal. Finally, we are cutting into wafers into 182 mm size square wafer. And now the industry is also moving from square wafer into rectangular wafer size. The wafer size is not same both the sides, and the width is 182, whereas the length is 191.6 mm. Or maybe some companies they also started doing 182 width and 210 is the length of the crystal. Of course, if you see here, there's a small change in the diameter. Normal 182, the diameter of the crystal is 247 or 250 mm diameter. And if you want rectangular wafer, you can slightly increase the diameter from 250 to 262 so that you can grow rectangular wafer. And by doing further increase in the diameter 272, you can even get 182 to 210. So what is the advantage of going with the rectangular wafer? So basically, a square wafer, the area, if you see the area of this wafer, surface area for 182, 182, it's a 478 square centimeter. When you go with the rectangular wafer, the area is increasing. When the area is increasing, automatically, the amount of current generated from the particular wafer also will go high. You can generate more power out of, one cell. So same thing for 210 also. And this is also another some few manufacturers they started using 210 where they maintain 300 mm diameter crystal from 182 250, whereas the 210 they are using 300 mm diameter crystal. So by changing the diameter of the crystal, they can also produce different size of the wafer according to their module panel design. So whoever are having their own wafer manufacturing capability, they can also produce different size of wafer. Accordingly, they can produce different size of cell size and module size so that they can increase the module power. So this is a competition, whoever having wafer facility, they have the benefit. And if cell manufacturer, India, mostly we have only cell and module manufacturing. We have to we have to depend on, import of wafers. So whatever the wafer size available, then we have to buy it. So we don't have the flexibility by changing different size of the wafer. So this is what, by doing recharging, by single crystal batch process only one time. If you do continuously feeding, then you can grow many number of crystals. By doing this, if you see here, okay, and the capacity of the furnace, because by doing the continuous pulling, instead of one crystal you grow 5 crystal, from one crucible, you are minimizing the downtime. The productivity also is increasing from baseline to almost 20% more productivity you can produce. And also if you see the cost, almost 4% of the cost per wafer cost also is going down. More importantly, productivity is increasing, right, by doing the different process. This is the different how they are going to refilling all those things. And if you see the maybe 2000 2004, maybe 10 years before, the crucible size, the crucible where you fill the polysilicon, it was 24-inch crucible. Maximum charge you can put kg. No, this is not that one. maybe 400 kg or 500 kg, something like that. And puller capacity, one puller, 2004, one puller can produce only 2.5 megawatt capacity equivalent ingots. But 2014, now see, after 10 years, the same kind of puller design, from 2.5 it can produce 11.5 megawatt of capacity. So if you want to set up a plant of 1,000 megawatt of manufacturing of ingot, the crystal pulling capacity, earlier you have to set up close to 300 400 numbers of pullers to produce 1,000 megawatt. Now even 100 and 50 pullers is even less than 100 pullers is enough, because the productivity has gone up by doing the recharging process and also increasing the crucible diameter. It was 16 inch, now the crucible diameter also increased to 32, and now 36-inch crucible, where you can load 3,400 kg of overall polysilicon you load. So more amount of polysilicon you load, more number of crystals you can grow. So automatically your capacity of the puller also will increase, and it is expected very soon 4,000 kg of polysilicon overall you can, at a time only you can load 400 or 500 kg, but continuously after one crystal load it again, so that overall amount of polysilicon you can use 4,000 kg, so that you can grow the capacity of the puller also 20 megawatt per year. Right. So significant improvement in overall equipment, capacity, so that capex number of pullers to produce certain quantity also drastically has come down. That will minimize your capex investment, capital investment. Disadvantage, another advantage of here, if you see here, continuous CC, this is a normal batch process, recharge process. There is a significant, improvement, operating hours. By doing continuous CC, you can reduce 40% of time you can save from, normal one crucible, one crystal, from one crucible, multiple crystal, 40% of time you can save, almost nearly 50%. Productivity also increasing. Another advantage is here, this blue color curve, one ingot you can, the resistivity variation across the top to bottom. As I said, top side always higher side, bottom side will be low. There's a huge variation from top to bottom if you grow one crystal. By doing continuous feeding, growing and also maintaining the volume, continuous feeding, you can maintain the resistivity also, because you know how much grown you have to add the dopant amount continuously, ensuring that the resistivity across the entire length is maintained. So by doing continuous CC, you can maintain the resistivity, so that when you convert these wafers into a next level cell process, the overall conversion efficiency difference will be relatively lesser compared with the single crystal. And if you see here, the carbon oxygen concentration also relatively maintain the same level, instead of going from top high low then high. The oxygen concentration level concentration also maintain low, and resistivity also maintain low. By doing the continuous CC, you can maintain all the performance parameters, so that you can get higher efficiency cells. But another disadvantage of doing this, okay, you can maintain the oxygen concentration, you can maintain the resistivity across the entire length. But when you go for large number of crystal, you cannot control the amount of impurities, because when you continuously feeding, the impurities of iron, copper, nickel, all these transition metals, because these transition metal will always try to be in the molten silicon. So when then first time when you grow the crystal, the amount of iron will be, concentration will be less in the crystal, in the grown crystal. When you use the second crystal, the amount of iron is going high, iron concentration, because you are adding more amount of polysilicon. Already the existing molten silicon also has certain amount of more impurities. When you add, then the amount of impurities, again the molten silicon will increase. So automatically when you grow number of crystal, you can maintain the resistivity, you can maintain the oxygen concentration, carbon, everything, but the metallic impurities or overall impurities concentration, you cannot maintain it. So there will be a drastic increase. So if you see here, when you grow, ingot length goes up and up, there is a chances of, at least the continuous CC process also, you cannot maintain the same level. There is a increase in the iron concentration that will improve your minority carrier lifetime, right? If you see the minority carrier lifetime also, but this CC process is still relatively better than one crystal. Suppose if you grow one crystal, right, or maybe continuous batch process, you grow one crystal, then load it, charge it again, and the amount of minority carrier lifetime, second crystal, third crystal, all those things, it will be relatively higher. When you go with the continuous CZ, still it is better than, still you are not able to maintain the same minority carrier lifetime across the entire length for all the crystals, but at least relatively, lesser, the degradation is lesser than the batch process or the charge process. So this one is the efficiency. When the minority carrier lifetime also changes, the conversion efficiency also will change. Of course, there is a slight compromise in terms of efficiency, but still overall, the continuous CC process is better than, batch process or this single crucible and this one. Okay. So, any questions, Thangavel?
Yes,
Should I
sir.
continue?
Sorry, the talk is more excellent, sir. So we never have this kind of talk until now. So talk is very nice, and silicon crystal growth is industrial orientation. Really, industry, semiconductor industry is going to get benefit from you, sir. The hands up this one.
Thank you,
Yes, sir.
thank you. And I have few slides anyway. This is the more. Then I go to the next.
Yeah, sir.
Field one.
Otherwise, just go through, sir. No problem, sir. I
I
think
think we
everybody
have time time out
yeah, sir.
now.
Sir,
Let me
time
stop
available.
here.
You can go through, sir. Few slides. No problem.
No. I think okay. Maybe I can, a few slides. I will talk about solar cell manufacturing. How this
Yes, sir.
quality, important for different cell technology. So this is what, how the wafer quality is more important for the cell efficiency, because you can improve the productivity of the equipments, and you can, grow more number of crystals, and still there is a, drawback from the first crystal to last crystal. There is a slight variation in terms of performance. So when you get the wafers from, if you do not have the wafer manufacturing, when you get the wafer from outside, obviously, you don't have a control. The resistivity, normally resistivity and everything same, but still there is a relative poor performance. That's the reason the Chinese, they always lead in terms of performance, in the efficiency, wattage, everything, because they have their own control of the wafer. They know the wafers produced from the first crystal, wafer produced from the last crystal, they segregate. Then accordingly they can tune the, solar cell manufacturing process. They can, so that they can minimize the degradation of first crystal wafer from first crystal to last crystal. So they can try to minimize the difference between first crystal wafer quality to last crystal, so that solar cell conversion efficiency also will be better. But for us, since we depend on wafers, depends on wafers from import, so we don't have any control. So whatever the wafer we get from China, so we have to convert into solar cell, and further module, obviously, the performance will be relatively poor. Then we are talking about the downstream two product cell and module. I'm not going to spend too much time. Maybe another 5 to 10 minutes I will spend. Then I'll close the talk.
Yes, sir. Yes, sir.
So
no problem, sir. You can carry on, sir.
no. It's almost 1.5 years.
Sir, we are very interesting, sir. It is not like that. It's just academic talk. This is pure industry. Everybody get benefits.
Okay. So when you talk about solar cell, there are different technologies available. So right now, maybe I can put the slide. So these are the colored ones are currently dominant technology, PERC and TOPCon HGT technology, and this one IBC and perovskite probably the future one, and the aluminum BSF, the old one, is completely outdated. And the module also, because the solar cell, once you make the solar cell, how you are going to convert the cell into module into different formats. Whatever the cell size, number of cells you can add, 72, 78, then monofacial, bifacial, glass to both the side glass, one side, one side, back seat. So different configurations available according to the market requirement. You can convert the cell into module into different product size, right? So this is the different, solar cell technology is available. So this is the one good, example where the world is, where you start, where you will end. The first, the solar cell produced in the Bell Lab in 1950s, around 50s, 1950s. That was the back contact. Back contact, N-type based back contact technology was the first solar cell developed in 1954 at Bell Lab, right? So that was the starting point of the solar PV cell device using N-type based wafer, not the P-type, N-type based wafer with the back contact technology. And after that, slowly the technology changed from N-type to P-type. Then P-type itself, there are so many changes happened, different design concept and all those things. From 1954 to 1973, different P-type based. The same 83 different P-type with a different efficiency. Then once again, 2098, then 2000, everything P-type based. But now the mono-PERC technology is a P-type which is dominant. Now the TOPCon and HAT, which I'm talking about the previous slide also, TOPCon and HAT, there is the advanced technologies, both are N-type based. So this is a good example where we started the solar cell technology N-type based back contact, and in between we moved the wafer from N-type to P-type with so many different designs to improve the performance. Finally we entered into the N-type, and now the future technology after this HAT and TOPCon, the future will be once again back contact. So where we started 1954 N-type back contact, and in between so many technology advancement here and there, finally the final solar cell technology also N-type based and back contact technology. So this is a very good example where you start, finally where you will end the same point, right? Yes, anyway, this actually, this solar cell, how the solar cell works. Basically, it's a band gap based silicon, has a band gap 1.13 meter, 1.13 EG, right? And whatever the, based on the band gap, the amount of sunlight, right? Amount of sunlight it can capture.
See, kindly mute.
Yeah, so amount of sunlight, because it can, convert into electricity, that, depends on the band gap of the material, what kind of material you're using. Silicon case 1.13. So though the sunlight spectrum, this is the bottom one is sunlight spectrum. So the sunlight spectrum is wide range, but unfortunately silicon can work only this area. Only this area silicon can work, and rest of the sunlight is going as a waste. But this side, anything on the UV side is a higher energy, but our silicon can work only up to 1.1 EG EV. So that means anything 1100 nanometer, any light falls on the silicon substrate or silicon PN junction, this will not be converted into electricity. It's going as a, it will transfer into the silicon. And
kindly mute participant. Hello.
Okay. So this one is, when we talk about silicon, we are talking about only single junction, PN junction, because this slide is very important. With this slide I will stop. This slide is very important one. This is the sun spectrum. As I said, this is the sun spectrum, right? And yes, whereas the silicon based solar cell, it works only here, particularly 400 to 1100 only it works, and beyond 1100 nanometer it will not work because the band gap is 1.1, and anything more than 1100 nanometer it will not convert, it will not able to produce any electron hole pair. So whatever the IR spectrum is going to be waste. And whereas the UV side, ultraviolet side, where you have a huge amount of ultraviolet in the sun spectrum, but the silicon works only this range, whereas this area the silicon is not at all, converting this light into the current. So whatever the light falls on that, because this is higher than 1.1, definitely, this will generate more amount of electron hole pair. But the UV light has very high energy. So instead of generating electron hole pair, it will also generate, waste of heat, excess heat also. Whereas also silicon also converting only certain portion of this one. So major portion of the sunlight spectrum, if you look at the sunlight spectrum, major portion is in this range, UV range, which is not effectively converted by the silicon based solar spectrum because of the limitation of the material, because limitation of the band gap. That's why if you see here, if you add another material over on this silicon, and that material will absorb this UV light and convert the UV light into the electricity. So by doing so, this is the solar, for example, cell 1, this is the first cell, top cell, the band gap of this material is very high. Then second material band gap is very low, third material further down. So by adding different material over on, this is the silicon, for example, silicon 1.1. If you add another material called 1.7, EV band gap, so automatically the higher band gap material work for the UV. It will effectively convert the UV light into electricity. So that by doing, multiple junction instead of single junction, you can add higher band gap material, over on that material, one PN junction, another material, another PN junction with a different band gap, another material PN junction with a different band gap, so that the top one will capture the entire UV spectrum, and whatever the left out, it will not capture the bottom side. So this will transparent to this top material, and it will enter into the bottom material. The bottom will convert this area, and whatever left out from this material, the red area, this area, the bottom one will convert the rest of the area. In this way, by doing this multiple junction, normally we call tandem junction, but doing so, we can effectively capturing the entire sun spectrum into the conversion, electricity conversion. By doing single junction, right now, whatever we have been talking about is a silicon based single junction, it can, convert only 23, 29, 28% only maximum. Most of the sunlight, sun spectrum is going as a waste, or you can generating heat when it falls on the silicon, it will generate more heat. So it's photon energy will be converted into heat energy instead of electrical energy. So by doing combination of different band gap, by you can effectively capture the sunlight spectrum, so that overall efficiency also will go up. So by doing the tandem cell, it doesn't need to be semiconductor. That's what I told the previous slide. Previous slide they're talking about perovskite. Perovskite is a thin film material. It has a different band gap like 1.7, 1.8. All these are 1.13 EV band gap material. But when you do the one more perovskite based PN junction over on the silicon. So silicon will be the bottom, perovskite will be at the top. So perovskite will work better in this area, and silicon will work up to this. So major portion of the sun spectrum here, IR, the sun amount of sunlight in the IR is relatively low. So major portion of the sunlight will be converted into photon energy into electrical energy, so that the efficiency will be, right now we are talking about 25, 26. This conversion efficiency will go to 30, 35, and if you add 3 junction, 4 junction, 35 will become 40, 45 also. So this is the way the industry is working on, instead of going with the single junction solar cell, they are going with the multi junction solar cell, and it's called a tandem based solar cell. I think with this I can stop here. Maybe if you have any questions, we can I can answer for you. Then
yes,
maybe
sir,
you can
yes, sir.
contact also by
Yes, sir.
over email for any further clarification. Okay.
Yes, sir. So thank you, sir. Thank you very much. This excellent talk for this industrial based solar cell and technology, how silicon will be grown using Sokolotsky techniques, the large puller growth. I think we welcome to the questions from faculty members and students. Yes, please. Any clarification, any doubts? Comments are available. You can discuss. Hello?
That's too late, right? 9 o'clock.
No, sir. It's not late. It's not. See, it's a talk is more. In my point of view, is I think everybody is enjoying talk. It's an excellent talk. Nobody, I never heard this kind of talk until now in my past 20 years experience.
It's okay. It's okay.
Sir, one participation asking, sir, you told sir N-type solar cell is started in the 1954, then again back to the N-type back contact. What is the reason why they are starting again? Like that, they're asking questions.
Okay, see, N-type, as I said, N-type started with the N-type, but during the production of N-type mono ingot is not that easy because it has a wide, resistivity range, and the growth process is a little bit difficult. So after the first, the solar cell technology evolved, after that, when the become commercialized, right? N-type wafer manufacturing was relatively expensive than P-type. P-type you can easily grow compared with the N-type, right? So the industry
Yes,
moved to the P-type. But as I said, P-type also after some time it has some limitation. You cannot minority carrier lifetime also you cannot increase more than 100 or 150 or 200 microseconds. Whereas the N-type based crystal or wafer you can minority carrier you can go up to even 1000, 2000 also. So in between the product becomes commercial friendly. Which technology, which wafer type is more commercial benefit, economically viable product. So that's why industry moved to P-type. Now that economic benefit of P-type is relatively lower than what you are getting in terms of efficiency. So there is a more potential in N-type products. So that like yesterday, the industry started with mono. This N-type also mono. Then industry moved to multi. And last 5 years, the multi is completely phasing out. Now industry is moving to mono type wafer. Even monocrystalline wafer, industry started with the N type. In between, they moved to P type because of the economic benefit. So that commercially, the product has to be commercially viable. So P type product are more viable than N type product because of the manufacturing cost. Now again, because the N-type wafers have better benefit in some potential in terms of efficiency, whereas P-type you cannot increase the efficiency to beyond certain level, right? Now the economic of N-type, if you have better higher efficiency, the power generation will be more, and wafer technology manufacturing process also a lot of developments have happened. P and N, so all these things put together, now industry is moving from N-type to P-type. Sorry, P-type to N-type. Sorry.
Yes, sir. Sir, one more audience from Rajeshwari from Tamil Nadu. She is asking question: how to identify the quality of EG or AG, or electronic grade and solar grade?
It's basically lifetime, because minority carrier lifetime. I shown some picture by seeing the surface structure itself. If the surface has lot of surface volume, surface area, more popcorn structure, that means in the growth process not happen properly, and when more surface area, there is a chances of more contaminations, because you are allowing the lot of gaps there. It will go and the impurities will go and sit there, and atmospheric particle also will sit there. When you have grown a very compact, very high density polycrystalline silicon, automatically less amount of, because the growth process also takes longer time. It's your slow growth process, right? So even the impurities, the dislocation, all those things will be better in electronic grade. And you can also measure the impurity concentration and iron content on copper, all the metallic industry. Also the minority carrier lifetime you can measure it. If the minority carrier lifetime is very high and iron content, carbon, everything is lower side, you can claim as a level in purity or electronic grade. If it's very minority carrier lifetime is poor, oxygen concentration, carbon is very high, you can consider as a solar grade polysilicon quality.
Yes, sir. Yes, sir. I think any other questions from the audience?
Sir, I want to say something.
Is it possible?
Thank you for
Yes,
sir.
yes. Please
giving
ask
a
question.
valuable-
No problem.
Sir,
Sir
is
is
it
ready
Thank
to
you,
say
sir, for-
answer.
Shall I, sir?
Yes, yes. Continue. No problem.
Sir, is it possible to arrive at silicon except from the standard methods?
Sorry, say again. I don't get you.
Except from standard methods, like ingot, preparation of ingot. Apart from that, is it possible to arrive at silicon?
Standard method means like a wafer or polysilicon.
So
Silicon.
those methods we are using to prepare silicon.
Growth
Is there any
method.
other method?
Growth methods, right? You're talking about growth methods.
Yes, growth methods or preparation methods.
And that's what, preparation method means. You see, solar semiconductor wafer preparation is different. That's what yesterday one of the talks they talk about how to prepare the semiconductor grade. After the growth method is same, but after slicing the wafer, how to convert the wafer, into the semiconductor fab application, the process is different. And here today solar wave after crystal, and how to convert the crystal into the wafer, solar application wafer, the process is different, very rough process, where there you need very high quality, polishing and all roughness and everything. Here solar grade, you don't need much process, it's a dirty process, quick and dirty process. But this is standard process available as of now. I don't see any other, wafer. Yesterday also we discussed there are two other wafer process where you can guess directly, you can convert the gas into the deposit on the substrate, and you can cleave that, a wafer, but that will be a very thin wafer, 10 micron, 15 micron wafer. This is very difficult to control the, difficult to handle that kind of thin wafers.
Sir, one more question. Sir, we have solar cells. The discarded solar cells, whether we are able to arrive at a pure silicon?
No, you cannot get the pure silicon, because already you have made the diffusion boron. The substrate itself comes with either boron dope or phosphorus dope. Only the pure polysilicon, the raw material only is pure polysilicon. After that, you are intentionally doping boron and phosphorus, converting into dopant. Then you are converting again, if it's a p-type wafer, n-type diffusion, so that p-n junction. So after converting into solar cell, you cannot get the pure polysilicon, pure silicon. Of course you can get it, but lot of chemical refining process. You have to take out all the boron, you have to take out all the phosphorus, all the other impurities. That's a cost intensive process, where the pure polysilicon is available much cheaper than this recycling process.
Thank you, sir.
Welcome. Yeah.
Sir, one fact, I think research scholar, she's asking one question, Amala Lakshmi. How does the material's electrical conductivity compare to the theoretical expectation? Like that is she asking.
Sorry, say again.
How does the material's electrical conductivity compare to the theoretical expectations?
No, how does
the material's electrical conductivity compare to theoretical? She's asking such a way theoretical resistivity compared to the experimental resistivity, comparing.
See, basically, still I don't get that point exactly.
No,
but
sir.
Still,
She is asking theoretical result and experimental results. Electrical conductivity.
see, electrical conductivity, normally that's what, maybe we define when pure polysilicon used, the amount of dopant material we add. So if you add more dopant, we know based on the growth process, pulling process, based on the segregation coefficient, we know how much amount of dopant will go into the, every stage of crystal growth. And if you know that kind of amount of dopant goes into that crystal, what would be the resistivity? Because silicon has, pure, then amount of dopant goes inside, then your resistivity also will change. So normally we we expect the range, the top to bottom, the resistivity will be 1.4 to bottom will be 0.4, top will be 1.1. We define the resistivity accordingly, we dope the dopant amount. But actual scenario, maybe sometime, you know, it will be 0.4 to 1.1, it may be 0.6 to 0.9, very narrow range, which is good for us. Sometimes because of some growth, you know, process variation, some disturbance in the growth process, probably it may go higher side of beyond 0.4, also 0.3, 0.2, also 1.2 also, which we cannot use. Of course we can use it, but generally, you know, any wafer resistivity going beyond that range, we cannot convert into solar cell. Then you have to optimize the solar cell process, right?
Yes, sir.
So actually we set the range. Most of the time we get that range, but sometimes it may go out of control. As I said, you know, when you grow multiple crystal, the last crystal may go slightly out of control.
Yes, sir. Yes, sir. Thank you, sir. Thank you very much. I think any other questions from any faculty members? I think Bharani Raj.
Hello, sir.
Yes.
Yeah, please, please.
This is Durairas. Sir, we
Yes,
will face
please.
radial temperature gradient during the growth.
Sorry, radial.
We will face radial temperature gradient during the growth. Temperature gradient radially.
Yes, definitely that will be
How
there.
we can overcome that, sir?
Yeah, because when you have any furnace, definitely,
Yes,
you know, axial as well as radial temperature gradient always will be there, but you have to, you know, minimize that range so that, you know, it will not impact the, see, because of that only even the resistivity also, if you see, I told top to bottom 1.1 to 0.4, even if we see radial also, right, radial also there will be a slight variation will be there, but that is, you cannot avoid it because it's a furnace, and you know, you're growing, definitely the radial side also temperature variation will be there, but you cannot avoid that one, but you have to minimize that one, you know, in such a way that it should not impact the resistivity distribution too much. The resistivity distribution, sorry,
how we can avoid that, sir? How we can minimize?
See, how you can avoid means, like, you know, you have a heated design and the gas flow, because you are growing in the environment, you're allowing continuous gas flow. How you flow the gas, how you extract the, you know, the residues gases out, and also the flow, the melt flow, whether it's a turbulence is happening, or how to maintain the flow within center region instead of, you know, more there are different types of flows, right? Instead of, you know, convective flow, you know, all those things, how to maintain that flow, you can minimize the temperature, you know, variation from the diameter of the crystal from wall to here, based on the gas flow mechanism, and also the heated design also, and with top to bottom, because we have a heater on the, not top, heater at the bottom and heater at the side. So how you design the, you know, heater power profile and all those things, you can maintain the, you can minimize the temperature. You cannot make it zero. That's impossible. Always there will be a gradient will be there, either axial side or radial side. But by controlling the gas flow and the hot zone design, you can minimize the, you know, radial temperature variation. As far as
is there any minimum scale to avoid this radial gradient, sir?
So
is there any minimum scale to avoid this? If you are going larger dia, there may be
yes,
gradient,
you're right.
is higher.
Yeah, you're right. When the diameter increases, when the diameter increases, definitely, you know, very difficult to control. So according, that's the reason, like if you see like a semiconductor growth process, I said, you know, they can go even 400, you know, diameter crystal, also even bigger than, you know, solar PV applications, but still they maintain this one by controlling the magnetic flow, because mainly they control the heated design, hot zone design, and melt flow. How the melt, you know, flows within the crucible, how to control the melt flow, uniform flow. But in the semiconductor case, they use a magnetic. They use a magnetic field. By using magnetic field, they control the melt flow, so that very controlled way the melt flow will happen. The growth process will take place, so that you can minimize the overall temperature disturbance in the melt, and also the impurity, incorporation from the crucible to here. In the solar, normally we don't use magnetic, but in the semiconductor, they use a magnetic field. So with that field, they can minimize the, the melt flow. The close to the wall, there will be a different flow, and close to the crystal, there will be a different flow. So that the outside, the impurities coming from the crucible will not get into this area. That way they can maintain the temperature and also the impurity through the magnetic field. But anyway, it's a different, equipment design and expensive also. So solar PV, we don't need that much, the high pure wafer. So for other semiconductor, you have to maintain very high quality wafer, in terms of oxygen, impurities, and also the dislocations, right?
Okay.
Yes, sir. I think this is very. Any other question from anything? Sir, I have one question, only one question.
Yeah, please.
Sir, the large size of crystal, for example, is 20 centimeter or 100 centimeter crystals. You are told it's a non-contact method that finding the electrical resistivity. Non-contact method.
No, you can also measure non-contact, or since it's a crystal, so you can contact. You can contact also. It's not going to impact anything. Anyway,
if you contact, then the crystal will be made little damage, right?
No, because it's a solid piece, 300 mm solid piece. So by touching the wafer, anyway you have to cut the piece, because you are going to round crystal only you are measuring. And after that, you have to slice all the 4 sides like this. You are converting the round crystal into the square crystal. So the touching the small probe, it will not make any kind of impact on the surface, crystal. Anyway, you are going to cut it, and even after converting into square shape, also still if you touch the squares of brick, it's not going to impact your damage. It's not going to damage any surface, because it's a very solid piece where the probe is very small.
Yeah, very small only.
Yes.
Yes, sir. I think thank you very much, sir. The excellent talk. I think once again thank Dr. C.V. Kannan. Yes, excellent talk.
Thank you so much, everyone.
Yes, sir.
Okay, nice. Pleasure of meeting
you. Yes, sir.
you.
Any questions, anything, then directly send to me or send to the Kannan sir also.
Okay, thank you.
Any questions, any clarification, any doubts?
Thank you, sir. Good night,
okay,
sir.
Thank you. Good night. Bye.
Thank you, sir. Thank you once again.
Snapshot, sir?
Yes, sir.
Sir, can we take a snapshot?
Yeah. Yes, we can take, no problem. You can turn on video, we can make 1 minute.
Okay, sir.
Okay. Thank you.